Hello, everyone. In this video, I will be walking you all through testing moderation using the common fate model. And so what we are going to do in this video more specifically is use structural equation modeling to using LMS interaction or latent moderated structural equations to test, again, the interaction um, between two common fate variables. And so the first step in this process is to kind of get familiar with the model that we'll be testing. And so I will scroll back up to the top momentarily, but what we are going to do is we are going to test the interaction between relationship mindfulness and dyadic coping in its prediction of relationship quality. So we are using the couples satisfaction index as well as the relationship mindfulness measure and one of the subscales from the dyadic coping inventory, right? So since we are using the common fate model, all of these effects and all of these kind of parameters and the way we're thinking about the model occur at the dyadic level or what is shared between partners. So again, in other dyadic analyses, the analyses are focused on the person level, my anxiety, my depression impacting my views on my relationship, how happy I am. But in this model, the common fate model, we are estimating the extent to which I am happy and to which that variance in me across the people in the study is shared with all their partners that are also included in the study. So again, it's modeling shared variance between dyad members. Again, it's focusing on something that is external to both members and it occurs between the dyad members. Right, and so I'll start at the top, and this will be a several step process. So we have all the variables in our Mplus file, and then we are going to be using a select few of them, including the dyadic or the common fate variables indicated by these 6 variables. So we're using a sample of heterosexual couples. And so we have dyadic coping and dyadic coping underscore M indicates female and male reports respectively. And then we will also have some covariates in our model, including relationship length, whether or not they have children, educational achievement of both partners, depressive symptoms for both partners, and both partners' ACE scores. Okay. And so before this analysis and before this video that I'm showing, I looked at some potential influential observations and we had some outliers. We had some people who apparently just clicked through the study based on their responses. They were exceptionally high on all the relationship quality variables, but they were exceptionally low on all the relationship mindfulness variables, which if you, based on the way they're scored, that is a kind of an indication that they were just kind of clicking through. And so what I've done is I've gone in and I have removed them. So I'll just dive specifically into the syntax. We have a ID variable. And again, this is a wide format. And so this is at the level of the dyad. So each row in our data file represents a dyad, and then we have a series of columns that indicate male reports on our variables and then female reports on our variables. And so when I am eliminating these cases, I'm eliminating both partners or both dyad members. All right, so it is not possible, at least within this current analysis, to eliminate just those single partners who may have just been clicking through, because it might actually be only one of the partners clicked through and one of the partners completed the study in a very intentional manner, and they were thoughtful in their responses. But for this analysis, we ended up getting rid of all those dyads. And so in here, I have the dyad ID. You'll see ID variable is specified here. And then it's not equal. And then 130 is the dyad number. And so to separate out the commands and to remove multiple people, I use the and statement. So this is, we are using all the observations in the data file that don't have a dyad ID of 130, of 358, of 159, so on and so forth. And we separate those out with that and statement, all right? And so what we're going to first do is use maximum likelihood to estimate the model without our LMS interaction term. Because as you'll see here in a few moments, we are going to use the integration algorithm, and that does not allow us to calculate fit statistics. And so what we first want to do is establish a good model before adding in that latent variable interaction term. And so right here we have our three latent variables that are all common fate variables. And so we have relationship mindfulness at the dyad level, and we constrain both partners' reports to be 1. So both partners are equally indicating our latent construct for relationship mindfulness, and that also applies to the dyadic coping and the relationship quality latent constructs or common fate latent variables. And so you will notice I have some code commented out. In the subsequent analysis, I'll add those back in because right now we simply just want to test the main effects of relationship mindfulness and dyadic coping on relationship quality. And then we are going to do that controlling for all of these covariates, okay? And so we also have those residual covariances that you would have in the common fate model. And so we have within person covariances. So that means the male report, so the male partner, their reports on relationship mindfulness, dyadic coping, and relationship quality are all covariate with one another to account for those within person effects or perhaps unmeasured common causes of possible residual covariances between them. All right, so that is the first model that that we are going to run. All right, and so what we can do is we can go ahead and run this model. And so what we are really going to be looking for is the R² value. That's going to be one thing that we'll want to look at. And we'll also want to look at model data fit. And so here we have our model data fit, our overall chi-square, 27 degrees of freedom with a chi-square of just under 47. So this indicates our model is generally well-fitting, even though this is significant, and we prefer for this not to be significant. Oftentimes the chi-square test is significant even in well-fitting models. It's a highly sensitive test. It is very, very powerful. So it'll detect even minute differences in the model data fit. And so again, even well-fitting models can be rejected according to just the chi-square. In fact, that was the precipitating factor for the creation of the CFI and the TLI. Back in the early days of Lisrel, this was really the only available fit statistic. And again, because it's so sensitive, people were often rejecting well-fitting models. So we will also consult the CFI and the TLI 0.98 and 0.95, again, by all traditional metrics that indicates decent fit. We have our RMSE of 0.05, which is good, generally at or below the cutoff, depending on kind of the RMSE value that you use. Some people say 0.05, some people say 0.06. Another good indicator of model data fit is that we have a relatively tight 90% confidence interval around the RMSEA. So if this was wide, if this was 0.004 and 10.3, then we'd probably make a slightly different inference. But since we have generally a fairly small confidence interval, we can we can be fairly sure that the RMSEA statistic is actually going to be fairly accurate. And so we will also scroll down to the bottom. And so we are going to take a look at residual correlations or covariances, and specifically look at the z-scores to see how well our model is reproducing the individual parameters. To me, this is actually a better indicator of model data fit, because if we have a lot of really high values here, then that indicates our model is expecting values that are substantially higher or substantially lower than what we're actually getting, which tells us we might have a misspecified model. So z-scores, their critical ratio is 1.96. And so anything above that is indicative of that is significant. And so we will look for those values. But again, due to the highly sensitive nature of these tests, especially around model data fit, I don't necessarily use 1.96 as a hard and fast cutoff. More so, I want to see, are there any outlying values? Are there any values that are, 5 or 10 or 15? If there's kind of these drips and drabs, if there are these 1.97, 2.02, 2.04, and they're all kind of clustered together, then that doesn't really worry me in terms of how well our model is or isn't reproducing the aspects of our data. And so we'll just take a look. And so we have, 2.02, 2.8, 2.8, 2.8, 2.4, 2.96, 2.7. And so 2.14. So we have a couple that are significant where, we're with a negative, we are underestimating, and with a positive, we are overestimating the parameters that the model would have expected. But again, I don't see anything here that is too out of bounds. I'm not seeing anything. Again, I think 2.87 is the largest one. And there's, several others within kind of they're close in kind of absolute value to 2.87, again, 2.45, 2.882. So that tells me that there's not one parameter that is just screaming at us. Rather, a lot of this might just be functions of just having really sensitive tests. So in this model, I am fairly comfortable with our z-scores, even though there are a few that are significant. And so all of this cumulative information that we're gathering indicates that we do have a pretty well-fitting model. Again, it's not a perfect fitting model. We'd still prefer that chi-square to be significant. We'd prefer those z-scores to be a little bit lower, but all in all, not terrible. And so we also want to take a look at our latent variable here in terms of variance explained. So we are explaining 73% of the variance, which is an exceptionally high amount of variance being explained by our model. So again, we have lots of latent variables in our model, and we have theoretically derived covariates. And so it is actually not all that surprising that we are accounting for 73% of the variation, in relationship quality, right? So these are things to kind of take into account. And the last thing that we'll want to take into account is our log likelihood value. So this value right here, because again, as I had mentioned before, when we use LMS and we have to use the integration algorithm, the only way to detect whether or not the addition of our latent variable interaction significantly improves the model, or perhaps doesn't improve the model, makes it worse, is through a likelihood ratio test using the H null values for each model. So what you will end up doing is you'll multiply these values by -2. And then you will subtract them from one another, where you subtract the null model from the model with the latent variable interaction. And then you will obtain a log likelihood value. And then you will, since we're only adding one parameter, which is the latent variable interaction, the difference test, or the D statistic that we're calculating by subtracting the log likelihoods from one another, it follows a chi-square distribution. And so we have one additional parameter. And so then we'll and the critical value for the chi-square is 3.84. So after we subtract the log likelihood values from one another, that value is greater than 3.84, then that tells us there is a significant difference in the models. All right. And with log likelihood values, it can be a little tricky because we actually want lower log likelihood values. The closer to zero, the better the model fits. The greater values, the worse the model fits. All right, so we have a good sense of how our model is fitting. We know our R squared. We have our log likelihood value. And so what we're going to do is we're going to exit out, and then we are going to come here, and we are going to remove some of these comments, and we are going to estimate our model with the latent variable interaction. So to specify LMS, you need to include type equals random. You need to include maximum likelihood. I'm still going to be using maximum likelihood throughout this. And then on the final model, I'm going to throw robust maximum likelihood in there before we get our final estimates, just to be sure that our model isn't overly affected by non-normality in our estimates and in our residuals. And the reason I don't do robust maximum likelihood throughout is that Maslowsky had a 2015 or 2016 article that talks about LMS interactions using Mplus, and they cite some simulation research where the model fit statistics in terms of the -2 log likelihood. They are better, they are more accurate when we are just using regular maximum likelihood compared to robust maximum likelihood. Right, so that is why we're using maximum likelihood in these model comparisons. All right, then we're also going to use the algorithm, the integration algorithm. So we need to specify that in our analysis command. And so in the model command, we will need to include or create, I should say, our interaction term. And so if you're used to the kind of the old way of just computing interaction terms with observed variables, what you might do is you might, in the define command up here, you might do int equals, x1 times x2, and that's how we create them. But that is not how we do it in the LMS, the latent moderated structural equations approach. We are going to specify it actually in our model command. And so I will give it a name. I'm just calling it int. You can name this really whatever your heart desires. And then you create a vertical pipe. And then you specify your IV and your moderator. And then rather than just the width statement, you use x width. And this tells Mplus that you are creating an interaction term using two latent variables. All right. And then we are going to also have our CSI outcome variable being predicted by the interaction term. All right. And so we need these labels here in order to create the simple slopes and to create our plots. And so I've just labeled them A1, A2, and A3. And I believe we are only going to be using A1 and A3. So you don't technically need this A2 label. I just throw it in there for my own sanity. And there are times, especially when you're testing multiple interactions in which you will need this. And so just out of habit, I have included this. All right, I will scroll down. And again, we have our traditional covariances. And actually, one thing you will notice up top that I have yet to mention is that in traditional interaction moderation, when testing moderation within like a linear regression framework or SCM, you covary your interaction term with your with your moderator and your independent variable. But in the LMS, you do not. If you actually try to covary this int term that we've created with your main effects, you are going to get an error message. In the LMS approach, it is presumed that latent, because the way it's constructed, that latent variable is kind of on its own. Essentially, not to get too into the weeds, is that we actually use finite mixture modeling or latent class analysis to create that latent interaction term, because even when you multiply two normally distributed terms together, it's going to create a distribution that's going to be exceptionally non-normal. And so what Klein and Moosberger did in 2000 in Psychometrica is they proposed that you can understand the non-normality that is created when multiplying terms together through a series of normal distributions using a latent class approach. And so that is how we generate our parameter estimates, standard errors, and things of that nature within an LMS approach. And so one of the requirements is that we kind of have that interaction term out on an island. So what we are doing down below is this is code that I did not go over in the first model, simply because we were not testing an interaction. And so this is using the model constraint command. I am specifying here the means of the moderating variable. And so I just use the tech4 output to estimate the means and the standard deviations of the latent variable that we're going to test at +2, +1, 0, -1, -2 standard deviations in relation to the mean. Okay. Another option is to standardize. You probably saw up top. You can standardize your coefficients before. Some people like standardizing their coefficients because it puts it on a metric that is interpretable. But I'm not doing that for a couple of reasons. The first is just conceptually, I don't really know what an interaction term means in terms of standard deviation units. It's hard for me to really reconcile what that latent construct or perhaps what that observed variable is if you are using more of an observed variable way of testing moderation. I just don't understand it. And even though our scales don't have a natural metric, kind of like height or weight does, what we can do is if we use the unstandardized effects, if we were to like administer these scales like as a clinician, and we see that we use the results of the study to see that, when people score at above 8.3 on the Dyadic coping inventory, that's when relationship quality begins to go up and up and up, and clinicians can actually administer that, calculate that, and they can actually use that in a more informed way, where the scores might actually mean something. And so, I'm a former clinician, and I'm still actually a licensed clinician. I just don't do a whole lot of practice. That to me is actually far more meaningful than standard deviation units. So for those two reasons, I actually go against the standardization method, at least when testing moderation. In other applications, I very much use it, but in this application, I am more likely to use the unstandardized effects. All right, so here again, +2. So I could probably actually comment this in. This is +2 SD, and this will be +1 SD. This will be plus 0 SD. This will be minus 1 SD. Whoops. Minus 1 SD and minus 2 SD. All right. And so I specify those. Those are just constants. And then here are the simple slopes equations. And so again, this is, again, very basic. And you will notice the A1 in here is the main effect that I specified above up here. So relationship mindfulness is my independent variable, and dyadic coping is my moderator. And so then I have the interaction term, and then I have it multiplied by the level of dyadic coping that we specified up here. All right. And so these are going to be the simple slopes. So these will be added parameters to our model. And then I want to plot those. And so we will use the loop function to capture those. All right. And so again, it's the simple slopes equations. And then we have our loop plot here. And then we have minus 10 and plus 10. That's the range on the graph that we're gonna that I'm requesting. And then we are also going to have the tick marks on the X and Y axis are going to be at 1 unit increments. All right. And up here, I am just telling Mplus, I want you to plot these five simple slopes, and I specify the equations down here. Okay. And so we can go ahead and we can run this. Hopefully, I've uncommented out everything I need to, but we'll soon find out. Of course, I missed something. We'll see what Mplus is saying. Parameter label or constant 0 must appear at the left-hand side of a model. That's right. Model parameter must be declared in the model command with new or plot options. All right, let's go take a look. And we will see what Mplus, there it is. The lack of I missed my exclamation point. So we'll see if that does it, and that did it. And so the LMS approach, it can take a little bit longer. Again, the LMS approach to interactions with latent variables is exceptionally computationally demanding and intensive. So it is not uncommon for these models to run for a minute or 2 or 3 or 4. And this is going to be particularly true if you are requesting diagnostics. So not shown in this video, I had kind of indicated that I had requested diagnostic using outlier and log likelihood and influence statistics. And those models run for 4 or 5 minutes on a relatively quick computer. So again, they are computationally demanding, so they are not going to run kind of like a standard like path model, for example. All right. And so we'll scroll down and I will show you kind of the output that we get. So here's our -2 log likelihood. And so again, this is the statistic we will multiply by -2 and then subtract from the first model in order to get the difference in the log likelihoods. And then we'll see if that number is greater than 3.84, again, due to the way we the interpretation of the log likelihood statistic. If it's greater than that, then that means our model is significantly better. Okay. So that means our log likelihood value, our increase or the difference between the two was greater than 3.84, which means that in reality it's lower and closer to 0, and so we actually want that value to be high. All right, so actually I will briefly pull up the Maslowsky article if I can find it. I had it pulled up. This might be it, but it might be my computer's using all my resources for Mplus. So, but I will put that in the video description on YouTube. So I'm not going to walk you through the formula, but I've already done the computation, and the difference in the -2 log likelihoods is significantly different. So the addition of the interaction term does not harm the model and actually improves the model data fit. Our log likelihood values are lower, they're closer to 0. Which tells us that the addition of the interaction term not only doesn't hurt the model, it actually makes it a little bit better, a little bit more parsimonious. All right, and so you can see here, again, using the unstandardized output indicated by just the model results right here, we have a significant interaction, right? And so we have significant main effects for dyadic coping, but not relationship mindfulness. And we can see that our interaction term is significant. And again, we can puzzle through our covariates. Some of them are significant, some of them are not, but that's of less interest since this is more based on implementing the LMS with the common fate model. And so we will scroll down and we can take a look at our new and additional parameters. And so we can see that at very high, high, and medium, the simple slopes tell us that there is not, that the interaction is not significant, right? So the slope of that line when dyadic coping is 2 standard deviations above the mean is not significantly different from 0. When it is 1 standard deviation above the mean, it is not significantly different from 0. When it is at the mean, it is not significantly different from 0. But when it is 1 and 2 standard deviations below the mean, it is significantly different from 0. So we do have moderation, and these are a more precise understanding of identifying at what values of dyadic coping is relationship mindfulness associated with relationship quality, again, at the dyadic level. All right. So again, historically, Mplus has not offered standardized output using LMS, but I believe this is a relatively new feature. And we'll again want to take a look at the factor loadings. Again, we did this briefly. I briefly kind of skimmed over it in the first output, but again, they're all at or above kind of 0.70, which is kind of the minimum requirement recommended for using common fate. So we're good there. I'm going to kind of skip over all of these effects because, again, to me, they're not all that interpretable. I don't know exactly what they mean because they're in standard deviation units. But what I am going to do is scroll down to that R squared. I also requested partially standardized effects since I do have some dichotomous covariates. So that is why STD is there. And so we have this. All right, this is really why we wanted that standardized output. So if you recall, in model 1, we accounted for 73% of the variance in relationship quality. And so in this model, which is identical in every way, with the exception of the addition of that interaction term, we now account for 83.4% of the variance, which means that the latent interaction between relationship mindfulness and dyadic coping accounts for 10.4% of the variance in relationship quality, all right, at the dyadic level. So again, that is a huge effect size. We very rarely in the social sciences get effect sizes this large in terms of moderation. Generally, we're happy with 1% of the variance or perhaps even 2% of the variance. So again, this is a particularly potent effect. And one of the reasons why is that I think there's allowing for measurement error to be attenuated and to be addressed using latent variables is going to be a big reason for that, because a lot of the times we're going to use measures that have 0.70, 0.80 reliability. And so when you multiply them together, you're multiplying that unreliability together too, and that can really obscure our effects to detect moderation when it's probably there more often than we think. So in this model, we are able to attenuate that measurement error, and we can actually model effects in the way in which we would describe them in an introduction, which is without measurement error at that latent level, at the level that we actually believe that they are occurring out in the real world, so to speak. Again, it's quite high, but in my eyes, not terribly unsurprising given the type of model that we are indeed running. All right, so what we can do now is take a look at the plots. And so we'll want to take a look at our latent distribution plots because we will want to take a look at how our variables are distributed, if for none other reason to just know our data. And I think that's so critical and so important. And many people have been hammered with pre-registration, not looking at your data, just running your models, and researcher degrees of freedom and replication crisis and all these types of things. And we're kind of bludgeoned with the idea of don't look at your data, don't make data informed decisions. And I think that's, that in a lot of cases, that's the right choice. But I think in some cases, that's not necessarily the right choice. So I always want to be informed so I can make an informed decision, not just be on one extreme or the other, where I'm constantly manipulating my data, or I'm not even looking at my data, and perhaps the removal of a single outlier that's not even a part of the population at which to generalize to actually makes everything work out much better. So again, I'm a big fan of looking at your data, looking at your distributions, testing for outliers, influential observations, and things of that nature. So we have some non-normality in relationship mindfulness. So it's again, we have a kind of a peak here, and we kind of have some non-normality in dyadic coping as well. And so we might want to think about throwing in robust maximum likelihood just to see if we would make any different inferences. But in order to really know that, again, here's our relationship quality latent construct, we actually need to look at the residuals of that. So because again, the assumption in structural equation modeling is on the normality assumption is at the residual level. So we need to, we would need to do that in order to be really confident in our ability to make sure sorry, my dogs are barking in the background, so my apologies. I don't know if you can hear them. To make sure that we are using the appropriate estimator. Okay. And so you can actually take a look at the distribution of our interaction plot as well. Again, we got some skewness. So if it was a little more symmetric, it actually wouldn't look half bad. But over on this left side, we have a few problems. But all in all, it doesn't look horrible. It ain't great either, and this is definitely nothing to brag about. So we will absolutely need to throw on robust maximum likelihood in order to adequately address this non-normality that we see in our marginal distribution that we are going to presume is occurring at the residual level, because there is a correlation between the two, what happens in the marginal and what happens at the residuals, but it's not deterministic or causal. So we are going to do that. So that's actually what we're going to do next. And again, we'll just want to pay attention to our standard errors of our model to see if there are any changes. So up back here, I'm going to throw in robust maximum likelihood right here, and I'm simply going to rerun the model. All right. And so this will take a moment in Mplus. And one of the kind of frustrating things about Mplus is once you hit the run, you can't really do anything else within Mplus until the model has finished. So we are kind of stuck waiting for the Mplus gods to cooperate and to fully estimate our model. Actually, while that is running, what I can do is I will pull up the Maslowski article. So here is the citation for the Maslowski article that walks you through how to estimate the LMS in Mplus. So essentially, it is the same procedure that I have walked you through here today. I did not go through the D statistic, which they will show you how to calculate. It's right here. And they provide guidelines, and they also provide some additional syntax. So again, this was a phenomenal resource for testing LMS interaction. Actually, normally it doesn't take this long. So actually what I'm going to do is I'm actually going to cancel this because it is taking longer than it normally does. But I threw on robust maximum likelihood, and it actually did not change any of the parameters. Our p-value was still less than 0.001. None of the, for example, like the relationship mindfulness main effect did not go from 0.077 before to 0.049. I think, in fact, the p-value actually went up to around 0.11 or something like that. And so there were some minor changes, but all in all, no substantive differences were made. Right. So the final step I would recommend is when you report these findings, use the simple slope plots. But I'd also recommend creating just an overall plot modeling all the simple slopes in a single graph. That way that the results become a little bit more interpretable, and they can be more easily communicated to the reader. So for example, I will actually pull one up really quickly. And this can be done in Excel. This can be done in R if you're an R user. And so there's a bunch of different ways to do it. I tend to be an Excel person. I'm making the shift into R a little bit, but I haven't fully immersed myself in there. So this is not the exact exact model that we ran, but this is essentially what it would look like. All right. You would want to model each of the simple slopes at the varying levels. Again, just to again make your actual interaction term a little bit more interpretable, because we can actually get easily fooled by these interaction terms, especially if you consider that our interaction effect was negative. Our coefficient was negative. I think our standardized coefficient was negative 0.33 or something like that. But you'll actually notice that when we looked at the simple slopes, there were positive values as when there was significance. And so again, that can make for an exceptionally confusing way to interpret. It can make it very difficult to interpret. So again, I strongly recommend displaying both types of figures. Again, the simple slopes, but also on an individual basis with the confidence intervals, which is what you saw. And then also plotting the simple slopes all on a single graph. So you can, again, determine what is the exact nature of the relationship, because you might actually interpret the moderation backwards if you have those sign flippages like we have in this model. So again, hopefully this has been helpful in walking you through latent moderated structural equations, the LMS approach, using dyadic data analysis. So thank you all so much for your attention, and I look forward to seeing you all again.